as bioprevent.
Really great to be on the other side, behind the scenes of the seminar series. It's really great to present today. So today I'll be talking to you about some insights from the laboratory scale on fire behavior in our state. And like Crystal mentioned, I'm assistant professor in the Department of Mechanical Engineering at UC Merced. All right, so to get us started, I wanted to contextualize just some information of wildfire activity around the globe to put our state into perspective, right? So as we've heard from many of the speakers in the seminar series, we've had some shifts in fire behavior in the past, in the recent history, right, where we've seen like these peaks in fire activity in the latter part of recent history, right? And our statistics regionally in the Western United States have also been increasing, right? So studies by Westerling and collaborators have shown that wildfire frequency has increased in the Western United States in the past 30 years or so. And in our state, we have some great data from CAL FIRE. I got this data from their publicly available data there. And we see an increasing trend in wildfires, right? Where we see the acres burned in millions has increased in the past 30 years or so as well. And in the past 10 years, we've seen also a very large shift. The data here is up to 2018, and I'm very curious to see the data up to 2020, which we know was a wildfire season that was especially impactful. Talking about the 2020 California wildfire season, we know that we had this dramatic increase in the amount of acres burned, right? Over 1 million, which we see here from the data here, that was a large increase from the previous year and from the 5-year average, right? So we're seeing overall in our state increases in the amount of acres burned in each of these fires, right? And a growth in the fire season duration that we have. Of course, overall, this is not new as far as the last 20 or 30 years. Our state is characterized by fire hazard regions around all throughout the state, really, right? Ranging from moderate to very high fire hazard, depending on the region that you are in. And very poignant for our state in particular is that we have large urban sectors, right? And because of that, because of population density, we know that we're getting a growth in the WUI, right? So these fires, when they occur and when they occur close to population, to human population, we have an increased risk to people and their property. We also know about the air quality and water quality impacts due to wildfires. We had some very interesting recent talks in the series about water quality and also on air quality, right? And we know from the combustion perspective that wildfire emissions will primarily be in the form of carbons and particulate matter and volatiles. And that depending on the type of emission and the emission rates will be basically the health effects, right? So ranging from respiratory problems to cardiovascular problems. And in addition to human health, we have also impacts to environmental health, such as the formation of aerosols and just things like impaired visibility when driving due to smoke, right? And going a little bit more regionally now to the Central Valley where I'm located in UC Merced, if we think back of the air quality that we had last fire season, that was quite impactful, right? So I got this data from the local air quality management district on their website. They have the daily air quality prediction, especially when we had those really large wildfires, right? And the data was showing us that right in the middle of this, we had unhealthy rather, air quality, and it was as easy as stepping outside to really see the data firsthand, right? Many of us were looking at these numbers from our comfy home offices, right, where a lot of us had our HEPA filters on. The moment that we see these numbers, we know that that's unhealthy. However, also here in the Central Valley, and as many of you might have seen in the news, there's outdoor workers, there were farm workers that couldn't be in home office working and were exposed to the air quality in already adverse respiratory conditions due to the pandemic. So there was kind of that double effect. So with that, I'll say that although I'm mentioning some as a background, some effects of wildfires on people and the environment, we've learned in the seminar series that there's also good fire, right? And particularly to our state, we have a history of good fire, such as the fire that has been used traditionally by indigenous peoples, and also in most recent history, prescribed fire, right? So as a fire behavior researcher, thinking about good fire and wildfire, and also the effects on people and the environment, I think about how do we predict wildfires so that we can better understand what will the behavior be and what will be potentially the risk to people and the environment. And so with that, some of the research questions that will be guiding my talk for today will be basically, what are some of the governing principles for fire behavior in our state? And I'll be talking about two particular regions. And in the first, I'll be talking about Southern California, Chaparral. Now, many of you might be familiar with fire behavior in Southern California. So I'll be focusing on a study focusing on Southern California, Chaparral Crown fire behavior. Then we're gonna move north, and we're gonna start talking about woody fuels and smoldering fire behavior in woody fuels, such as what could potentially happen in regions with high tree mortality, such as certain places of the Sierra Nevada. All right, so in today's talk, I'll be focusing on two of the features of the fire behavior drivers that we know as a community are governing wildfire behavior, and we know that those are fuels, topography, and weather. Today, I'll be asking the research question with regards to fuels of how do fuel properties and fuel configurations affect fire behavior? Again, I won't be talking about topography, but I will be talking about weather effects, right? And in particular, I'll be mainly looking at how do wind-driven fires behave, and how does this behavior compare to that of non-wind-driven fires, right? And as all of you probably know, fires are very complex. They happen on multiple lengths and time scales. For this talk, I will be focusing on the laboratory scale. So this scale over here. And so the time and length scales that I'll be talking about are pertinent to the lab. All right, so to start, I'll talk about the first project, focusing on Southern California, Chaparral. And the co-authors for this study, that I did this work during my PhD, and the co-authors were my advisor at the time, Dr. Marco Princivac, and my lab mate, Amir Hassam Aminfar, and at the USDA Forest Service, David Weiss. All right, so first I'd like to put into perspective for those who might not be too familiar with fire behavior in Southern California, in that chaparral shrubs are basically cover around 5% of California land. And Chaparral, because of that, essentially Chaparral is the primary fuel for wildland fires. So a lot of the fires happening in Southern California are Chaparral fires. And in this region, again, like I mentioned before, proximity to large and urban and suburban sectors construes an increased risk to people and property in the event of a Chaparral fire. And one example here of fire in Southern California was when I was a student there at UC Riverside, we had a fire right behind campus near the Box Spring Mountains. And so that's an example of how close people are often to where these ignitions happen and where we might have some spread. All right, so if we look at the behavior of chaparral fires, we can think of them as crown fires. And by that, I mean crown fires as defined as fires that might be initiated in the surface, where surface fuels are dominated by dead and dry, thin fuels. And then once we get an ignition there, we might transition to the canopy, or sorry, the elevated fuel layer of our shrub, also known as the crown fuel layer, right? And in this case, we might have some chamise. And so this transition from surface fuel to crown fuel layer is an important feature of these types of fires. And the subsequent spread is also an important feature. So in this talk, I'll be talking about chaparral fires as crown fires. There's been previous studies looking at fire spread and crown fire ignition in chaparral. A lot of that work done alongside in UCR and the Pacific Southwest Research Station of the USDA Forest Service. I have some of the studies here. And these studies have looked at the ignition and spread characteristics, but mechanisms of spread in both layers, so the surface fuel layer and the crown fuel layer, at the time when we were first starting this study, were not thoroughly understood. And to preface some of the work that I'll be presenting and just to contextualize or motivate some of the work that I'll be talking about, because it's some basic science, I wanted to give a motivation that is more applied, right? So as we all know, simulation models are very necessary for management and planning. And we know that currently existing models like Farsight or Behave Plus, which are used operationally, are based on the Rothermel model. And the Rothermel model is based on assumptions of a homogeneous single layer fuel bed composed primarily of thin fuels. So for researchers like myself who are looking at fuels in our state that are not fitting these assumptions, the challenge is to understand the basic fire behavior to fill the gaps from these models, so we can essentially come up with more accurate descriptions of these fuels and fire fuel systems, right? So we can provide perhaps some improvements to fire model performance. So that's part of the motivation and the more applied motivation for the type of work that I'll be presenting today. And the very specific research objectives that we had when we started the study was essentially to quantify the effect of parameters that I'll be explaining in a second of crown base height and wind on flame geometry and burning rate in order to understand the amount of interaction between the surface fuel layer and the crown fuel layer. I also wanted to examine some crown flame geometry so that we can compare to currently existing models of flame geometry that have been obtained semi-empirically to understand how closely are those matching to our systems and if we can derive semi-empirical models to explain the fire behavior of chaparral fires as dual layer systems. So again, I'll just summarize. In the work that I'll be presenting, the chaparral crown fires are being modeled as dual layer crown fires. All right, so before moving on to showing you some data, I wanted to show, to talk a little bit about crown fires for those of you who might not be too familiar with crown fire behavior. And I'm gonna try to situate here my screen so that I can make this a little bit better for myself. Okay, right, so as many of you know, fuels in the forest are typically categorized in ground fuels, so below the surface fuels such as roots, right? Then we have surface fuels, these dead and dry fuels, thin fuels on the forest surface. Then we have crown fuels. So those are the elevated fuel layers in the forest. When we have an ignition in our surface fires, that might or might not ignite our canopy fuels, right? And a type of crown fire that you might be more familiar with than chaparral crown fires is that happening in larger trees, such as in this picture where we have the surface fuels igniting, and then we have the canopy fuels catching on fire and then subsequently spreading. This is a similar behavior to what we would observe in chaparral crown fires. So a very important feature of studying crown fires is studying their ignition criteria, right? Because we're coming from the assumption that the first thing that will ignite is the surface fuels, and we're trying to understand whether that will jump to the elevated fuels, because we know that because the elevated fuels are live and have higher moisture content, the energy output from these fires would be larger than that from surface fuels. So this transition is very critical when studying crown fire behavior. We know that from theory that ignition of the crown fuel layer will be dependent on things like the surface to crown distance, so the distance between those two fuel layers, also known as crown base height. Also the intensity of the fire growing under the canopy, right? The surface fire intensity. And the surface fire intensity is a way to measure the heat output, the thermal heat output from the surface fire. And you might commonly know this as the BRM fire intensity, in which we have fire intensity defined in terms of rate of spread and the weight of the fuel consumed times a heat of combustion for the particular fuel, right? So in the previous slide, I talked about ignition conditions, right? So we might have minimum ignition conditions to ignite the crowns. I didn't mention here, but flame length is another important parameter, right? So whether our flames will be able to ignite the elevated fuel layers. So that describes some of the surface fire ignition potential for the crowns. Aside from the ignition question, in crown fire, it's important to talk about the spread question, right? So what happens after the crowns ignite? And that's where I like to base myself on the Wagner model, which is the classical model of crown fire behavior, right? So in the Wagner model, we have three types of fire: passive, active, and independent fire, where passive and active crown fires, in those two, the surface and the crown, the crown fuel layer is dependent on the surface fuel layer for energy and fuel mass transport. So for example, in the passive crown fire case, the crown depends on the surface for energy delivery. And you see here in the schematic that I put in here, the the surface fire usually preheats the elevator fuel layer so that it's easier basically for the crown fuel layer to be spreading. In the case of the active crown fire, there's still that dependence, but it's more of a partial dependence on the energy delivery from the surface fire. The crown is able to supply some of its own energy to spread. In the case of the independent crown fire, and this is one of the rare cases of crown fires, we have a case where the crown does not require the surface fire to supply energy, right? So from a heat transfer perspective, that's a rare case because it means that the crown has to have sufficient energy to spread in itself without requiring, for example, preheating, right? And so this theory essentially tells us that the surface and the crown fuel layers are highly dependent on each other, right? And so when we study these types of fires, being able to model those two fuel layers as independent fuel layers will enable us to capture that energy exchange. And so when studying crown fire behavior, it's important to ask the question, basically, which of these parameters will be governing the type of crown fire we're obtaining, passive, active, or independent. So motivated by some of this theory, we ran a set of experiments at the Pacific Southwest Research Station at the USDA Forest Service in this wind tunnel that has been developed alongside the USDA Forest Service and UC Riverside. We ran these experiments where we've modeled these chaparral crown fires as dual layer fires. So we have the, if I can grab my laser pointer here, we have a surface fuel layer with dead fuels. In this case, it's Excelsior. And then we have a live fuel layer made up of chaparral. And we ran a series of experiments that test the effect of the surface to crown distance and the effect of wind on the spread of fire and ignition of the crown fuels. So again, we were running these experiments in this large-scale wind tunnel where because of the fact that we wanted to model this as dual layer fires. So one of our goals was to characterize burning rate from each fuel layer. And most other studies had characterized burning rate in the surface and ignition up to the crown. In order for us to be able to characterize the spread and burning rate in the crown fuel layer, we designed this custom-made mass loss system where we equipped this cantilever beam that we have here where we support our crown fuels with load cells that measure instantaneous mass loss. So that enabled this adaptation enabled us to measure mass loss in both fuel layers. And then the bottom, we had a standard scale that we can just place under the surface fuel bed. Sorry. All right. So we also had temperature probes, so thermocouples all through our fuel beds. I won't be presenting the temperature data today, but we did measure temperature loss for each fuel bed. Right. So like I mentioned before, we were looking at the effect of crown base height, wind conditions. So we ran wind-driven fires and non-wind-driven fires, and those were our experimental parameters. We kept a constant mass for the crown fuel layer, so we used 2 kilograms and of chaparral, and we burned Excelsior, half a kilogram of Excelsior underneath the crown. I'll say that the chaparral was collected locally in the area around in the Inland Empire. in a place called Beaumont. So we would usually collect 24 hours, within 24 hours of the day of burning in order to maintain moisture content. And so we would collect 24 to maximum 48 hours, and then we would burn. And we would pre-treat the fuel, such as to remove branches that were larger than a 1/4 inch diameter to maintain uniformity in the fuel bed. We measured flame geometry through videography, and we also measured fuel consumption with the instrumentation that I mentioned before, a custom mass loss system and a standard scale for the surface fuel. All right, so this is a picture of a typical experiment. So we ignited the fires at the surface fuel. So we would soak the leading edge of the surface fire that I have my laser pointer here with alcohol. Then we will ignite with a torch that leading edge, so a line fire through the surface, and then simultaneously, while the person was finishing igniting and closing the wind tunnel doors, another person will turn on the fan for those experiments that were wind driven, and then we would allow the fire to naturally grow. So the fire would first spread through the surface, and then eventually would naturally transition to the crown. And we would allow the fire to spread and until it would lead up to residual smoldering and then end. We measured a few things, but one thing that we measured was time to transition. So for time to transition, so the time between when the surface fire was ignited and when the crown fire ignited, we found that for the no wind cases, when the crown base height increased, the time to transition actually decreased. And for the wind-driven fires, as the crown base height increased, the time to transition increased. We also looked at burning rate for our configuration. So for the effect of the crown base height, we found between cases with 60 and 70 centimeter crown base height, we found that there was an increase of about 31% for wind and driven fires. And then when we increase from 60 centimeters to 70 centimeters at crown base height, we saw an increase in burning rate of about 85%. We also looked at, so I'll skip this one. So we also looked at crown base height effects for, I believe this is the surface fire, where we saw a decrease in burning rate. So we characterized the flame height for the top layer, for the crown. And there we saw an increase with wind. So the cases that are C are non-wind driven fires at 60 centimeter distance between the surface and the crown. And E are the same crown base height, but wind driven fires. So C is no wind, E is wind. There we saw a 70% increase when we added wind. And in the case when we had the distance between the surface and the crown was 70 centimeters, we saw an increase between non-wind driven fires and wind driven fires of about 84%. Okay, I think I will skip this one. Right, so another thing that we did was to try to model flame heights, or rather to see if we can derive a semi-empirical model that relates flame height to heat release rate. And that's important because works such as those by Sun and collaborators have shown that for Chamise Chaparral, we have some correlation between heat release rate and flame height. And in this case, their data showed a 2/5 power law relationship. So we ran a similar test and we found that their models fit our data well within the model performance that we have here. And we also tested another model that had another type of power rule that's similarly regressing the burning rate to the flame height, and that also fit our data quite well. The next thing we did is we wanted to understand whether we could do some FROUDE number modeling to explain the behavior in our system. And I'm loading this quite fast so that we can see here. But for those of you who are not familiar with the FROUDE number, this is a non-dimensional number that relates the relative importance of inertial forces to buoyant forces in a system, right? And for that reason, it's particularly important for fire behavior. And quite important for the type of fires that we were studying is that there are some known correlations between flame tilt, which can influence things like radiation, heat transfer to the fuel, unburned fuel. So flame tilt is correlated often with FROUDE number through some semi-empirical correlations. And so we ran some tests in our data and we found semi-empirical correlations that related our flame tilts for some representative experiments to a FROUDE number power law. All right, so in summary for this study, we looked at how crown base, height, and wind and non-wind driven fires were affecting fire behavior in our system. We found that crown base height affected time to transition. We also found that time to transition decreased for cases without wind. We also found that wind promoted mass loss rate by increasing the mass loss rate in essentially all cases, and that's somewhat expected. And we were able to fit some semi-empirical models of fire behavior for flame tilt. And important to this is that we were modeling our fires as dual layer fires. So we were able to capture that energy dynamic between both fuel layers. All right, so some ongoing work. We are currently reviewing some available work because we want to characterize the rate of spread that we obtained from our experiments and to compare the rate of spread that we've obtained prior to transition to the crown and after to transition to the crown. And here we've some of the reference studies that we've been looking at, and some of the ongoing work right now is we're developing an algorithm to do image analysis in order to convert basically from videography of the flames to a rate of spread measure or for our experiments. And this is ongoing work in my group. All right, so with that, I'll transition to the second project that I wanted to talk about today, and that's related to smoldering fire behavior in woody fuels. And this is work that I started during my postdoc at UC Berkeley. So the co-authors from this study are Carlos Fernandez-Bello, Michael Gorno, Luca Carmigiani, Franks Richter, Christina Livertu, and Han Yu Seong. Right, so to give some background on this study, and we're talking about, let me just go back here. We're focusing on basically the central and southern Sierra Nevada and woody fuels that result from massive tree mortality. So because of that, I wanted to give a little bit of background on the changing landscapes in the Yosemite Valley and in general in the Sierra Nevada. So I really like this image because it really shows how the Yosemite Valley has changed, right? So we see from a very sparse composition in the mid 1800s, and we start seeing how that composition increases in density, in tree density, up to current time where we have this very dense tree population in the same region. And we know from more of a fire behavior aspect that as forest structure changes, what we're changing is the fuels that we have to propel a fire. And in this case, when we have this shifts in the composition of the forest, we're increasing the amount of forest fuels and potentially also increasing the amount of surface fuels. So this may lead to increased fire intensity when we have larger amount of trees, and also an increase in crowning potential. Something very important that happened in our state was reported by this report by the USDA Forest Service, where they did a survey of tree mortality in the state from 2010 to 2018. And they found that around the year 2016, there was a massive peak of tree mortality that you see here. And actually, when you look at the map, this tree mortality event that happened around that time happened to occur here in the central and southern Sierra Nevada. So what the survey surfaced was that in the southern and central Sierra Nevada, there was a massive tree mortality event that was most likely caused by a bark beetle outbreak. And this massive tree mortality event basically resulted in the death of more than 100 million trees. And the accumulation of the fuels on the forest floor can essentially result in changes to fire behavior because of this shift in the fuel regime, in the surface fuel regime. And to understand how fire behavior will be altered, we first must examine the behavior of these large woody fuels, right? So what do we know about tree mortality and fire? Let me remove this laser pointers. Apologize, it's a little distracting there. So some things that we know about fire behavior in large woody fuels is that they're typically characterized by longer burn periods. They're also more likely to smolder, right? And unlike fine fuels, smoldering combustion in large fuels may continue burning through fuels after the flaming front has passed, in a phenomenon known as post-frontal combustion. And most of the models that we have in our understanding of fire spread comes from a flaming fire, right? I have an image here adapted from Franzen, where this theory by Franzen, or this was used to derive a lot of the currently used rate of spread models. And there we're assuming these fuel beds composed of thin fuels, homogeneous fuels, and under flaming combustion, right? However, smoldering fires have some important different characteristics. So in case some of you might not be too familiar with smoldering fires, I included here some pictures of some more recognizable smoldering fires, such as cigarettes, peat fire, and certain types of biochar. All right, so smoldering fires are essentially different types of combustion as compared to flaming fires. And what we know from combustion here is that essentially, when we have pyrolysis, as we all know, we have fuel that reacts with heat, and we get, as a result, pyrolysis, char, and ash and other solids. After we get pyrolysis, so that gasification of our fuels, we have two routes we can go, either the smoldering route or the flaming route. Most of what we're familiar with is the flaming route, right? Where we have the products being a pyrolysis gas and oxygen and things like CO2 and other gases. In the case of smoldering fire, the char that is produced from pyrolysis reacts and forms products like CO2, other gases, and diverse products. So the difference here is that smoldering is a solid state reaction, whereas flaming is a gas state reaction. And what's very important for macro scale fire behavior is that smoldering fires are known to have lower peak temperatures, lower heat release rates as compared to flaming fires. We also know that smoldering fires can be ignited with weaker sources than flaming fires. So because of that, smoldering fire tends to be longer burning than flaming fire. Also, because of the requirement for this weaker ignition source, the issue of transition to flaming becomes very important. So when we have transition from smoldering to flaming, because smoldering requires a weaker ignition source, that transition may actually represent a shortcut to flaming, as some have called it, right? So another feature of smoldering fires that is very important to recognize from a macro perspective is that emissions from smoldering fires are different than flaming fires, and that smoldering fire is typically characterized as a more incomplete combustion than flaming fire, right? And also we get particulate matter release, so in the solid state. We know from some previous work that the CO to CO2 ratio in smoldering fires, which typically is used to understand the completeness of combustion in fires, is typically for smoldering fire around 0.4, whereas for flaming fire, that number goes down to around 0.1. So smaller CO to CO2 ratios are representative of flaming fires, larger ratios are representative of smoldering fires. So with that, our mission here was to measure a few things and trying to characterize the behavior of smoldering fuel. So we were trying to measure the CO and CO2 emissions during smoldering combustion, and we also wanted to quantify smoldering burning rate and potentially smoldering to flaming transition. And we wanted to test the influence of fuel structure and wind speed on burning behavior. And we did this through a number of bench scale wind tunnel experiments. We also took a novel approach to follow others in the recent literature to model our fuels using cribs in order to control structure and porosity. And I have a couple slides showing a little bit more information about the cribs. All right, so these were the experimental configurations that we used. This is a bench scale wind tunnel experiment where we run our study. And here you see that we placed our, let me use my laser pointer here. We placed our fuel bed inside of the test section of our wind tunnel. And we instrumented the wind tunnel with a load cell apparatus that had some special adaptations, so we can place it under the wind tunnel and be able to obtain the instantaneous burning rate and mass loss of our crib. We used an anorak system, which can be used for emissions measurements. So we were probing the emissions from our experiment. And I have some pictures here of some experiments where we have our crib placed inside of the wind tunnel during burning. Right. So like I mentioned before, we followed others, very notably some recent work by Sarah McAllister in using cribs to model wildland fuels. And cribs are, for those of you who are familiar with compartment fires and building fires, cribs have been used for a long time as ignition sources for building fires. And these are these wooden structures that you see here in the picture. And one of the benefits of cribs is they're somewhat sort of like Legos, where you just construct them to very set geometries, and you're able to control the porosity and the geometry of the system quite well. So these make for very good fuel beds for fire behavior experiments, because you can very thoroughly characterize the fuel bed essentially. So you can characterize the porosity and the configuration. So this make for highly controlled fuel beds for fire behavior experiments, and they've been recently used for wildfire fuel modeling. So for that reason, we use cribs made up of poplar dowels to represent our smoldering fuels. Because we were testing the effect of wind, we used various wind speeds. So we have a low speed wind tunnel at the Berkeley lab. So at the UC Berkeley lab, I'm sorry. So for that reason, the maximum wind speed was 1.25 meter per second. The lower range was 0.5 meter per second. And we controlled for the fuel moisture of the cribs by oven drying the fuels for about 24 hours until we achieved a moisture content of less than 1%. So this helped us maintain uniformity in our fuel beds. Right, so this is a picture of a representative experiment. So you see here inside of the wind tunnel, the initial crib configuration before we start the burn. And then once we set up our experiment, the next step is ignition. And something that we adopted in this study is to ignite first in the flaming regime. So we open the wind tunnel top and we soak with alcohol. Then we ignite with a torch, and we allow the flame to fully engulf the crib, and the flaming fire is allowed to naturally transition to a smoldering fire. When the transition is observed, we covered the wind tunnel, turn on the wind tunnel, and started the anorak for the emissions calculations. Sorry, the anorak was started right at the beginning, but the substantial portion of the emissions data was during the time that the wind tunnel was covered, right? So you see here the evolution of the experiment from the initial configuration to the ignition to the evolution of the flaming regime to the smoldering fire. And the fire was allowed to combust in the smoldering regime until we observed that smoldering essentially slow down and stop. All right, so here are some results from typical experimental data set. So for each experiment that we ran and each experimental configuration, we calculated mass loss rate, the CO and CO2 emissions, and we calculated the CO to CO2 ratio. For the entire experiment, we gathered data for the flaming and the smoldering regime, but because the wind tunnel top was open during the flaming portion of the experiment, we did not do the analysis over the over the flaming regime. We only focus it primarily on the smoldering regime. So most of the data was cropped here at the onset of smoldering. Okay, so some observations here for the first set of experiments, so the preliminary data set. So we have an updated data set that is currently in review for a manuscript, but this is before that second stage. In the first stage, we were testing the burning conditions under the various different wind speeds, and we found somewhat expected behavior of increasing burning rate with increasing wind speed. So the emissions in that preliminary stage were decreasing for CO and CO2. And we also observed CO to CO2 ratios that were closely aligning to what was expected from the literature, right? So as I mentioned right at the beginning, CO to CO2 ratios are of about 0.4 are typical in smoldering fire. So that's what we were observing in our experiments. All right, so some conclusions from that study. I'll just highlight a few from the list here. So the first, from the preliminary set of experiments, we found that we can essentially use these wooden cribs to model these types of fuels. And we also found that the most efficient way of igniting was in the flaming regime and allowing it to naturally transition to smoldering. We found the increasing the wind speed enhanced the intensity of the smoldering combustion rate, and that increased the smoldering burning rate and the wood mass loss in our system. So with that, here I also have some information on our CO and CO2 ratios that closely align with the literature. And with that, I just wanted to finish off with some notes on other ongoing California wildfire projects in my lab. We currently are working on a study focusing on the air quality effects of the 2020 wildfires on the Central Valley. So we're looking at air quality and emissions coming out. Sorry, I had a timer there for myself. Coming out from the 2020 wildfires and how it affected our region here in the Central Valley. We are setting up our first burn in the lab, and that is, we've been planning and setting up our experiment, and that's going to be ignition of wildland fuels by metal particles. The work on smoldering fire is continuing. We're still doing a lot of analysis on the Chaparral Crown fire data for rate of spread analysis. And ongoing is some fabrication and design for our fire wind tunnel for my lab at UC Merced. So in the summer, we'll be fabricating and testing our fire wind tunnel. So that's going to be very exciting once we can launch that in the lab. And before I finish, for those of you who are Star Wars fans, happy May the 4th. And with that, I leave you with acknowledgements for the different groups that have supported my work and the collaborators that I've worked with. And with that, I know I just have a few minutes. Sorry, Crystal.
Oh, that was a fantastic presentation, Jeanette. And I am personally very excited about the wind tunnel burn lab being up and running. So this is going to be fantastic. So we'll actually go ahead. There's currently one question in the Q&A, and we'll go ahead and move that over to the discussion because it is 1 minute till 4, and we do have to move over at 4 o'clock to the other, the discussion room rather than staying here in the webinar room. Oh, maybe this is an easy yes or no question. I am curious if the fuel moisture content was controlled or accounted for with these lab experiments. I imagine it is very difficult to control this since the chamise is being collected from field on demand. that an easy answer, Jeanette, or?
No, yeah, that's a good question. Very good question. We measured it. We did not control for it.
Okay, so for those of you that have more questions or just want to hear more about the group that Jeanette is building at Merced and amazing fire behavior work going on, please join us. The link is in the chat, and if you go ahead and just click on that right now, we will be moving over to the discussion. Next week is our last week of the seminar for this year, and we will be hosting Dr. Joe Scott from Pyrologics and looking at the new risk assessment for fire risk assessment for California that he has just completed with his group of collaborators. So please make sure you join us next week. And for now, we look forward to seeing those of you that want to talk more about fire behavior over in the Zoom discussion. Okay, and stop recording. Stop recording.